Okay, so in the previous class, we were discussing tunnel diode. Okay, right? What way tunnel diode is different from ordinary diode means it is heavily doped. Okay, right? It is heavily doped. So, what do we mean by heavily doped? Okay, the impurity concentration is of the order of 1 to the power, okay, means in 1000 atoms, there is one impurity atom. Okay, so that is heavily doped, whereas in ordinary PN junction diode, in 10 power 8 10 power 8 atoms, there is one impurity atom. Okay, right? So just in 1000, right, in 10 power 3 atoms of silicon, you have one impurity atom, right? Okay, so because of this impurity, okay, ratio, this particular device is heavily doped. Okay, right? And we know very well when doping is high, the width of the depletion region is thin. Okay, right? And when the width of the depletion region is thin, right, then what happens? The charge carriers can easily tunnel through the depletion region. Hence the name of the device, tunnel diode. Okay, hence the name of the device, tunnel diode, right? And in the previous class, we were discussing the energy band diagram, right? We have seen this in the previous class. Fermi level, that is the energy level occupied by the, okay, electron. It is the highest energy level occupied by electrons at 0 Kelvin. Okay, in simple words, above Fermi level, you don't have any, okay, electrons, right? Within the solid, there are no electrons above the Fermi level. Okay, that is EF. So what happens here is, means up to EF there are electrons. Okay, so the electrons I am representing by the shaded portion. Okay, so till on the P side, up to this level, okay, there are electrons. And here we can observe that the Fermi level I have drawn constant. Okay, right? See, Fermi level is not constant, then charge carriers will move from one direction to another direction. Okay, so far we did not apply any voltage to this. Okay, we did not give any supply. That is called as no bias condition. Okay, such a situation is called as no bias condition. Okay, what is the meaning of no bias condition? We did not give any supply. Okay, right? This energy band diagram, which we are now considering, it is for the case of no bias condition, means we did not give any voltage. Okay, then Fermi level is constant. Highest energy level of the electrons is constant. Okay, what it indicates is there is no transfer of charge carriers. Okay, if energy level is not constant, for example, okay, right, if you have water constant, okay, then there is no flow. Suppose at one level the water is higher compared to other level, then the water flows from high level to low level. Okay, same logic. So here, okay, under no bias, we know very well that we don't give, when we didn't give supply, the, okay, current is zero. Current is zero means flow of charge carriers is zero, right? Okay, flow of charge carriers is zero simply means all the, okay, all the electrons, right, the highest level of electrons is constant. Okay, I have given you the water example. Okay, suppose there are two waters. If they are at the same level, there is no flow from one body to other body. If suppose, okay, water at one point is higher, then it will flow. That is how your rivers are flowing, correct? Okay, they are flowing from high area to low area. Same with electrons. Okay, simply remember electron is like, in terms of energy band diagram, electrons is analogous to water flow. Okay, right? So next, so this is under no bias condition. You know very well that in the P region we have holes. Okay, so where the holes are, they are in the valence band. So this is where the holes reside. Okay, in the valence band, okay, the valence band is not completely filled with electrons. You can see there is vacancy here. Vacancy is nothing but holes. Okay, so all this region above Fermi level and below EV on the P side, above EF and below EV on the P side, this is where the holes reside. Okay, so here in this region we have holes. Okay, in that region we have the holes. Okay, correct. Fine. So this is the energy band diagram under no bias condition. Always the difference between the conduction band and the valence band is known as energy gap, EG. Okay, right? All this we have seen, right? So first Fermi level is constant, right? And there are holes in the valence band. So we are drawing EV above Fermi level. Okay, what it means is, valence band, there are vacancies. After that vacancies only you have electrons. Okay, right? Electrons will always occupy lowest energy, right? You know, 1s2, 2s2 orbitals, okay, right? Within the atoms, how the electrons occupy. First, the first orbital, once it completes, then only you go for the second, right? Lowest energy is occupied first, right? After 1s, then only you go for 2s, right? Okay, so obviously the vacancies will be at the higher compared to the electrons. So keeping that in mind, see, keeping this visualization in mind, to understand that we are representing diagrammatically, that is this energy band diagram. Okay, right? So first Fermi level is constant, and you know in the valence band there are holes. So definitely, okay, on the P side, the valence band we have to draw higher than the Fermi level. Always the conduction band is above the valence band, because only when the electrons come out of the valence band, they come out of the atom, then only the current flows. Okay, that is what we mean by conducting, right? Okay, so it is actually coming out of the atom, right? When electron will come out of the atom, only when we give additional supply. So obviously always EV will be, okay, lower than EC, or EC will be higher than EV. Next is, what about N side? Already in the, okay, already in the conduction band, right? You have the charge free electrons, isn't it? So to represent that, EF is the point till where you have the free electrons. Okay, so in the conduction band you have to have free electrons, means EC should be below EV in N side of the, okay, tunnel diode, right? So electrons we are representing by this shaded energy gap, right? Okay, you know, planets around the sun, they go in orbits, right? Okay, so there is definitely gap, otherwise the planets collide, correct? Disaster happens. That is not happening because there is gap, same inside atom. Okay, right? There is gap, energy gap, where there are no electrons. Okay, that is Eg, right? So keeping all that in mind, this is the energy band diagram. Okay, so to make it easy for you, what I have done is I have drawn this once again. Okay, same diagram, right? Same diagram. I have drawn this once again somewhat neatly. Okay, right? So now let us see what happens. Okay, now let us see what happens inside. Okay, inside the tunnel diode. Okay, when we apply bias, remember this is no bias condition. What we have just, what we are now seeing, this is no bias condition. Okay, so what I will do, I will pull out this somewhat lower. Okay, and then I will write here. Okay, okay, let me write here no bias condition. Okay, I will do one thing. So this is the no bias condition, Fermi level is constant. Okay, right? Now next part is very, very easy. What happens when we give biasing? Okay, right? What happens when we give biasing? Okay, see, for this you have to understand one simple point. Okay, suppose now here, okay, we know very well that this is, okay, p side and this is n side. Okay, let me write that one also. Okay, 8 minutes. I have indicated here, right? Okay, so this is p side of the energy band and then the n side of the energy band, right? The only thing now you have to remember is, okay, as I told you, this is no bias condition. No bias condition is not given in your question bank. Okay, only what happens under reverse bias, what happens under forward bias is given. Okay, but without this, I don't think you can understand that. So I have, okay, given this, right? So now what happens when we apply, okay, what happens when we apply reverse bias? Okay, right? So first, under reverse bias condition, okay, right? So what do you mean by reverse bias condition? So now what I will do, next I will go for the case of reverse bias. Okay, next we will consider the case of reverse bias. So what I will do is, okay, I will take this, okay, I will copy it and then, okay, I will edit and let you know what happens under the reverse bias condition. Okay. Okay. So as discussed, this is the case under no biased condition. Okay. So under reverse bias condition, okay. Now here you have to understand what happens to the energy levels. Okay, right? See, what do we mean by reverse bias? Reverse bias means on one side, okay, right, compared to the other side, we are, okay, P side we are connecting positive, right? That is what we mean by reverse bias. Okay, reverse bias means you know very well. PN junction, general PN junction PN junction diode reverse bias. So what do you do? P side negative, N side positive, you connect. Okay. So next what we will see is we will consider the case when you connect P side negative and N side positive, how the energy band diagram shifts. Okay. So next, considering the case of reverse bias. Okay. Next, considering the case of the reverse bias. Okay. So this is the PN junction, right? Under no biased condition, but this is under no biased condition. Now what we are discussing is how this diagram modifies for the case of reverse bias condition. Okay, that is what we will be discussing next. Okay, so under reverse bias condition, N side we are connecting positive and P side we are connecting negative. Okay, right? See here, suppose inside if you connect negative, then the energy of the electrons will further increase. The energy levels will simply shift upward. Okay, right? So inside, if you connect negative, the energy, it is like this. Electrons are negatively charged. To that negative, if you connect negative supply, the energy levels is shift upwards. Okay, but when you reverse bias, means inside when we connect positive. Okay, when we reverse bias, means N side we connect negative. So what happens? The energy levels will go down. Clear? Okay. So the only thing you have to remember here is the shifts in the energy levels. Okay. So first, this is no bias condition. I hope you have understood. This one I will now edit and we will go for the case of reverse bias condition. Okay. right? So this was no bias condition. Now we are going for the case of the reverse bias condition. What happens? Okay, so let me put the heading reverse bias condition. Okay, so as I told you, reverse bias means inside we connect positive. Okay, you know very well that inside we connect positive means reverse bias. So opposite, when you connect the energy levels of this n side, they will go lower compared to that of the p side. Okay, right? See, electrons already negative charge. To negative, if you give negative, the energy goes high, right? But when we give opposite, okay, that is for the n side, when we give positive voltage, which is reverse biased, then the energy levels will simply shift downward. Okay, so what actually happens under reverse bias condition means, okay, this is very easy to represent here. All these energy levels, they will shift downward. Okay, right? You keep on giving reverse bias, the energy level keeps on shifting downward. Okay, so I hope all of you are able to notice that now the energy levels, they are shifted. Okay, just to focus this part. Under reverse bias conditions, what happens on the n side? Okay, on the n side, the energy levels, they shift downward. Okay, so I've shown slight downward, right? Okay, so as a result, what happens? Okay, as a result, what happens here is, okay, now see the portion above the line that I have drawn. Okay, I have drawn a line matching the Fermi level on the n side. Okay, I have aligned a line on p side. I have aligned a line on p side such that that line matches the Fermi level on n side. Okay, so above the line, whatever the electrons you have, okay, above the line, whatever the electrons you have, okay, those electrons, remember this shaded, whatever I have shaded, those are nothing but the electrons. Okay, right? So whatever I have shaded, those are nothing but the electrons. Okay, right? So this, the entire shading in color, okay, the entire shading in color, this one and then this one. All these are nothing but the electrons. Okay, right? All these are nothing but the electrons. Okay, anyway. So above the line, whatever the electrons that you have, okay, above the line, you have electrons, right? Okay, all these electrons on the p side, now they see empty states on N side. Okay, right? So again, this is like water flow. Okay, again, this is like water flow. At one side, the water is higher compared to the other side. The water will flow, right? As long as you give supply, this is higher compared to this, the water will keep on flowing. Okay, so that will constitute to current. That will constitute to the current, right? And now, if you give further reverse bias, okay, if you give further reverse bias, all the energy levels on the N side, they keep on going lower compared to P side. Okay, right? As a result, the number of electrons that can now tunnel through the junction will keep on increasing. Okay, so that is the reason. If you see the characteristics of the tunnel diode under reverse bias condition, the characteristics of the tunnel diode, they are like this. Okay, so characteristics of tunnel diode under reverse bias, okay, condition. So you know very well that is, this is forward voltage, okay, then forward current. Under reverse bias condition means this quadrant, okay, you know very well, right? So under reverse bias condition, as you keep on giving reverse bias, okay, this energy levels on the N side, they keep on going lower. So more number of electrons can tunnel. As a result, as a result, what happens is the current will keep on increasing. Okay. Okay, right. So these will be the characteristics. You keep on giving the reverse bias, okay, the current keeps on increasing, right? Now let us see what happens under forward biased condition. So under forward, see, under reverse bias condition, okay, what we have considered, this particular N region, the energy levels in the N region, they go below the P region, right? This is what happens under reverse bias. So what do you think will happen under forward bias? Under forward bias, the N region will keep on going higher with respect to P region. Okay, right? Let us see that situation also. So next, we are again going back. Okay, we are again going back from reverse bias condition to no bias condition, means Fermi level is constant. Then, okay, so I am doing control Z. So control Z means we are going back to, okay, no bias condition, right? Fermi level is constant. Now next, let me consider what happens under, okay, forward biased condition. Okay, so I will now consider the case of forward biased condition. So I will change this to, okay, I will do one thing. I can type here. Okay, so I will type Okay. So what happens under forward biased condition? Simple. Under reverse bias condition, the N region kept on going below. Now the N region will keep on going above with respect to P region. Okay. So the situation will be like this. So let me give, say, some small amount of, okay, some small amount of forward bias. Okay, some small amount of forward bias. Remember, we are now dealing with the case when the tunnel diode is forward biased. Okay. Now what happens? Now again, let me draw a straight line which indicates constant Fermi level. Okay. Right. Now, if you see what you can observe, the Fermi level on the, okay, the Fermi level on the N side is higher compared to P side. So the charge carriers, the electrons will flow from N to P. Okay. Now say this is my EV on P side, EF on P side, EVEF on P side. Next, EFEC on N side. So the situation is now like this. If you keep on increase forward bias, at one point maximum tunneling takes place. Then further, if you increase forward bias, the gap between these two reduces, so the tunneling reduces. Okay. And after certain point, it behaves like a ordinary PN junction diode. Okay, right? So depending on